The recursive revolution, mastering self-calling algorithms in modern programming. In the ever-evolving world of software development, recursion has emerged as both a powerful tool and an enigmatic concept. This self-referential approach to problem-solving allows developers to break complex tasks into smaller, manageable subproblems through function calls that reference themselves. The beauty of recursion lies in its ability to simplify intricate computational challenges by leveraging the call stack mechanism inherent in most programming languages. From traversing tree structures to solving mathematical problems, recursive algorithms have become indispensable in modern algorithm design and implementation. Fundamental concepts behind recursion. A recursive algorithm is defined by two essential components: the base case and the recursive step. The base case serves as the termination condition, preventing infinite loops by providing a concrete solution to the simplest form of the problem. The recursive step involves reducing the current problem size while maintaining the same structure, eventually reaching the base case. This process resembles peeling back layers of an onion until only the core remains. Base case. Without a well-defined base case, recursive functions will continue calling themselves indefinitely, leading to Stack Overflow errors and program crashes. Recursive step. In this phase, the function must solve a slightly simpler version of the original problem before returning control to the previous caller. Each recursive call creates a new frame on the call stack. Consuming memory resources. Properly structured recursion ensures that each level of the call stack contributes meaningfully to the final solution. Misimplemented recursion can lead to excessive memory usage and performance degradation. Classical examples of recursive algorithms. The factorial calculation provides one of the earliest examples of recursion's elegance. To compute n, we simply multiply n by n1, with the base case being 0 equals 1. This simple formula reveals how recursion naturally models mathematical expressions that are inherently repetitive. Similar patterns appear when calculating Fibonacci numbers, where f(n) equals f(n1) plus f(n2). Understanding the call stack mechanism. When a recursive function executes, each invocation adds a new frame to the system's call stack. These frames contain local variables, parameters, and return addresses crucial for resuming execution after the recursive call completes. The last in first out, LIFO, nature of stacks means that the most recent function call is always the first to complete. As each recursive layer unwinds, intermediate results propagate upward through the call chain. For example, consider calculating factorials: factorial 5 dash factorial 4 dash factorial 3 dash factorial 0. Once the base case returns, the computed values begin aggregating back up the call stack toward the initial invocation. Performance considerations. In recursive design. While recursion offers elegant solutions, it often comes at a cost in terms of time complexity. Many recursive implementations exhibit exponential time growth, making them impractical for large input sizes. Tail recursion optimization can help mitigate some of these issues. When a recursive call appears as the last operation within a function, certain compilers and interpreters can optimize the call to reuse existing stack space instead of creating new frames. Time complexity. A naive recursive approach might result in 2 to the power of n operations for problems like Fibonacci sequence computation. Spatial complexity. Deep recursion depth can consume significant stack memory, potentially exceeding system limits and causing segmentation faults. Identify opportunities for memoization to avoid redundant calculations. Consider iterative alternatives when dealing with large datasets. Evaluate whether tail recursion optimization is supported in your target language. Common pitfalls and how to avoid them. Newcomers to recursion frequently encounter issues such as missing base cases or incorrect parameter adjustments during the recursive step. These mistakes often manifest as infinite recursion or logically flawed outputs. To prevent common pitfalls, programmers should adopt systematic debugging strategies including print statements, visualization tools, and unit tests specifically designed for recursive functions. Advanced applications of recursion beyond basic mathematical computations. Recursion finds profound applications in data structure traversal and search algorithms. Tree traversal techniques like inorder, preorder, and postorder rely heavily on recursive methodologies. Graph exploration algorithms also benefit from recursive approaches, particularly when implementing depth-first search, DFS. By recursively visiting adjacent nodes, DFS efficiently explores paths within connected graphs. Comparative analysis, recursion versus iteration. While both recursion and iteration can achieve similar outcomes, they differ significantly in their underlying mechanisms. Iterative approaches typically use explicit loop constructs with clearly defined termination conditions. Recursion, on the other hand, relies implicitly on the call stack, which can make code harder to debug but often leads to cleaner, more readable implementations for certain types of problems. Space efficiency. Iterative methods generally require less memory overhead since they don't create additional stack frames with each iteration. Readability. For problems that naturally decompose into smaller subproblems, recursive implementations can be more intuitive and easier to understand. Optimization techniques for recursive algorithms. Memoization represents one of the most effective ways to enhance the efficiency of recursive algorithms. By storing previously computed results, we eliminate redundant calculations and reduce overall runtime complexity. Dynamic programming builds upon this principle, using tabulation or memorization techniques to store intermediate results systematically rather than relying solely on function call caching. Memoization example. The classic Fibonacci sequence becomes significantly faster with memoization, changing its time complexity from O(2 to the power of n) to O(n). Dynamic programming approach. Rather than repeatedly computing the same subproblems, dynamic programming pre-computes and stores all necessary values upfront. Implement cache decorators for automatic result storage in functional languages. Create lookup tables explicitly in object-oriented programming paradigms. Analyze trade-offs between memory consumption and processing speed. Modern implementations and language-specific features. Contemporary programming languages offer various features that aid in writing efficient recursive algorithms. Some support tail recursion optimization automatically, while others provide specialized syntax for handling recursive data structures. Languages like Haskell and Scala embrace immutability principles that align well with recursive thinking. Functional programming paradigms often encourage recursive solutions over traditional looping constructs. Functional languages. Lisp dialects utilize recursion extensively due to their list processing capabilities and homoiconic nature. Object-oriented languages. Java and C++ allow recursion but require careful management of stack depths to prevent overflow exceptions. Case studies. Real-world recursive applications. The quicksort algorithm exemplifies how recursion simplifies complex sorting problems. By partitioning arrays around pivot elements and recursively sorting subsequences, quicksort achieves average case linearithmic time complexity. Fractal generation represents another compelling application domain. Mandelbrot sets, Sierpinski triangles, and Koch snowflakes all demonstrate how simple recursive rules produce incredibly complex geometric patterns. Quicksort implementation. Choose a pivot element, partition array into left and right segments, then recursively apply quicksort to those subsets. Fractal generation. Define base shapes and replacement rules, iterate through generations applying transformation rules recursively. Educational strategies for learning recursion. Mastering recursion requires deliberate practice and conceptual understanding. Beginners should start with small-scale problems before tackling larger, more complex scenarios. Visual aids play a critical role in grasping recursive behavior. Diagramming call stacks manually helps reinforce how information flows through successive function invocations. Pedagogical tips. Begin with simple arithmetic sequences before progressing to tree traversals and graph algorithms. Practice recommendations. Solve puzzles involving Tower of Hanoi, binary searches, and directory file systems to develop spatial intuition for recursion. Future trends in recursive algorithm development. As parallel computing architectures evolve, researchers explore novel ways to harness concurrency within recursive frameworks. Divide and conquer strategies may soon integrate distributed processing capabilities. Machine learning integration presents exciting possibilities, enabling adaptive recursive algorithms that modify their own logic based on real-time feedback and performance metrics. Parallel processing, recursive divide-and-conquer techniques could leverage multi-core processors for simultaneous subproblem resolution. Adaptive systems, machine learning models might dynamically adjust recursion depth thresholds depending on hardware constraints and task requirements. Conclusion recursion stands as a cornerstone technique in computer science, offering elegant solutions to seemingly intractable problems through self-similar decomposition strategies. By mastering the art of recursive thinking, programmers gain access to a vast repertoire of problem-solving techniques applicable across diverse domains, from artificial intelligence research to financial modeling simulations.